So for example number 5, we're going to do the reverse. We're going to transform the equations that are given in Cartesian coordinates and make them look like polar. Well, in this case, these are a lot easier to, number 1, visualize and convert because, well, we're given x's and y's, and all we use is the corresponding x and y definitions of sine and cosine, our r cosine, r sine. Well, so the first one, 2x plus 3y equals to 5. What kind of equation is that?
Linear?
It's a linear equation, right? And also we're going to use, okay, let me rewrite them. X equals r cosine and y equals r sine. Okay, so all we do here is replace x with the corresponding expression r cos theta and y with r sine theta. That's all we do here. That's really, yep, it's pretty straightforward. Yep. And that equals to 5. Now, so the next step is to solve for r, because these functions of theta are r equals some function of theta. So let's factor out r, 2 cosine theta plus 3 sine theta equals to 5. And well, r equals to 2 cosine theta plus 3 sine theta in the numerator of 5. And there's really not much else to do. Letter B, the same. I mean, x times y, multiply the corresponding expressions for x and y respectively. So that's a 6 times r cosine theta, r sine theta equals to 7. Well, this will give us a 6r squared. I'm just going to write sine times cosine. And solve for r squared first. That's 7 over 6 sine theta cosine theta. Right? And well, you could leave it like this, or of course you can take the square root and get a plus minus square root of 7 over 6 sine theta cosine theta. Okay? And I mean, of course, you can split it between the negative and the positive, list both of them. And all right. So for letter C, there's a couple of ways to go about this one. So number 1, well, actually, this looks exactly the same as the one that we did before. But now we're gonna do this backwards. So I mean, you could replace x and y with their corresponding r cosine and r sine, but that's going to make our expression look really big. So let's keep it in terms of x and y's for now, using the binomial squared formula. And well, the real trick here is to have together the x squared and the y squared. And then I'm going to move, okay, number 1, notice how the ones cancel. And x squared plus y squared minus 2x equals to 0. And x squared plus y squared equals to x. All right? No, that's fine. That's fine. Oh, okay. No, that's fine. But number 1. What's x squared plus y squared in terms of radius and angle? Isn't that r squared? And then replace x with r cos theta. That's r squared equals r cosine theta. All right? Now, we can simplify this equation right here. This is something we are we are not allowed in algebra, but we can do it in the polar world. Oh, I'm missing a 2 here. All right, we can do it here. Let me explain that. For example, let me just take a real side trip real quick. Oh, no. How would you solve this algebraic equation? X cubed over x. X cubed equals to x. What would be the first step to solve it? Divide by x. Alright? Okay, divide by x. That's going to give us x squared equals to 1. And x equals plus or minus the square root of 1. How many solutions is that? But what's the degree overall? We would expect to have 3 solutions, right? So in fact, well, this is the incorrect way to do it. In fact, we have to have all terms on one side of the equation factor and in fact, well, this means x equals to 0, x equals to 1, and x equals to negative 1. So there's our 3 solutions, and the reason why this is incorrect, it's because the minute we divide by x over here, we are potentially dividing by 0. Are we allowed to divide by 0? Because in this case, x can take any value except 0 because of the division by 0. And well, in fact, it happens that one of the solutions is 0, so the minute we do it, we are actually doing that division by 0. However, in the polar world, it's possible to do this because the radius can be 0. So that's why we can do this division. Okay, what's next about? Okay, the next is just a summary of the different common polar curves. This is something that you are not expected to memorize. Let's just have a look at the different forms. R equals to A, it's a circle of radius A centered at the origin, and well, R equals A sine and R equals A cosine. Well, depending on what function you have, we have shifted circles here. You can relate this to if for some reason you were to memorize this, which, well, I don't see the point of memorizing this. Well, a circle that is shifted vertically, well, think of the trigonometric function sine to describe the y component, right? In this case, well, we can relate the shifting in the vertical direction, and at the same time, the cosine represents the x-coordinate of the point in a circle, the trigonometric function world. Well, so it's sort of the same way here. It's horizontally shifted circle, one that has the cosine sign. We have the limmasones. We have graphs of cardioids that looks like a heart. That's why it's called cardioid. Other kinds of limmasones and flowers and roses, rather. And there is a very important thing to keep in mind when it comes to the graph. So if for some reason you want to graph you want to memorize the graph of a rose, and well, so these are of the form A sine n theta. Whenever n it's an odd number, well, the resulting rows will have n leaves. For example, cosine of 3 theta is going to have 3 petals, in this case 3 leaves. All right, and but in this case, like cosine 4 theta, this is an even number. Whenever you have an even number, it's going to have twice as many petals as the coefficient that multiplies the theta. In this case, 4 theta, notice how we have 8 petals in total, right? And you can play with this graph. So let me put the graphing calculator. And in order to do this, be sure to have in polar mode. So go to mode. Yesterday we were working in parametric form or parametric mode. Let's this time go to polar mode. Okay, click enter. And now go to y equals and see how the function that you will type are not going to be y1, y2, y3, etc., nor a collection of x1, y1 for parametric. This time we're going to have r equals something, So let's plot, let's say 2, okay, before, so 2 cosine 5 theta. Okay, how many leaves would we expect before clicking enter? 5. Let's find out. It's there. 5. All right. And you might want to zoom a little bit. Zoom in. Yes. Well, it's going to look a little bit sharp right here with sharp corners. Of course, we can window and the theta step, make it a little smaller, 0.01. Hopefully that helps. And it's also going to take longer to plot because the calculator here, it's doing more calculation, it's thinking more. And that's a better graph, right? Notice how, well, you can think of this as the main leaf. Do you see this main leaf is being extended along the x-axis? That's because we have a cosine function. If, okay, let me change this to a sine and see what happens. Change that to a sine. Do you see that main leaf now extending towards the vertical axis? All right. So another thing, well, how about, okay, second insert a negative sign. Let's see what happens. Now it's going to open in the negative direction, right? Because of that negative sign. So basically the same patterns on shifting and transforming functions from regular algebra are connected here in the polar world as well, right? And okay, what about, let's make this, okay, let me change this to and let me delete the negative sign, and what I'm going to do, sine of 8, no, maybe not 8, yeah, let's do 8. How many leaves will that flower have? 16. Let's have a look. There you go, 16 leaves. Right? That's what it is. And I mean, of course, you can play with this and have pretty cool images right here now. Of course, there's other fun curves. There's, I mean, the cardioid that you saw there, it sort of looks like a heart, but it's not quite a heart. Let's look at this one, a butterfly curve. Okay, let me do the butterfly. Let's type the butterfly, the equation of a butterfly. Oops, yes, it's here. Okay, so it's e to the sine theta minus 2 cosine 4 theta. Whoops. Minus 2 cosine theta. Oh, 4 theta. And there's our butterfly here. Zoom standard to 6. Well, maybe zoom in. No, maybe zoom fit. There you go. And it's a little sharp. Alright, it's a little sharp. I mean, it's spiky. So, window. Oh, yeah, you might want to change this to 0.01. Much better. And it's going to look for sure much better. A lot better. Let's look at the actual Valentine curve. For the actual Valentine curve, okay, I'm gonna do this one in a slower motion here because there's a few commands that we need. First of all, number one, we need absolute value. The absolute value will be found under math. Scroll once to the right, to highlight the num function, and the first one, that's the apps. Click enter and then type the tangent function, tangent theta. Then raise this to another absolute value. So go to math mode. Oh no, just math, not mode. Math num apps, and oh, what's going on? Second quit. Yep. Oh, okay. For whatever reason, I quit it. Okay, so math num absolute value of cotangent, but well, we don't have a cotangent command in our calculator, do we? But we can use trigonometric identities to represent that cotangent using a different command. Which one would be? Tangent, 1 over tangent, so 1 over tangent theta, but don't forget to close parentheses. And you're going to have a double heart here. All right. Yes, of course, these equations, I mean, are pretty complicated. They don't have the form like the ones at the top of the page in the summary. These are ones I found on the internet, so I was like trying to find other kind of fun curves. I mean, of course, you can play with your calculator and get the other one. There's another way to get the Valentine curve, and there's even the Pac-Man curve, so let's see the Pac-Man curve. Clear. What was that? 1 plus cosine to the 999 cosine theta, close parentheses, and raise to the 999. And graph. Well, it looks like a Pac-Man with a tail, but I mean, nothing's really perfect. Maybe zoom in a little bit. Oh no, that's not. Okay, zoom fit. Yeah, zoom fit is better. And it sort of looks like Pac-Man curve.
I didn't have them. Wasn't it?